Cam, here I seem to have a little PSC logo. Now what are we going to do?
Yeah.
Yeah. Okay. Are we?
Just do your entire screen.
Okay, how's it look?
No, I'm understanding, but it looks like they're having trouble getting it turned on.
We're good.
You think it's on now?
We're good.
Yes.
No. Those little signs with the lines to the camera and the microphone don't count.
No, that's too. Okay, so we're live, Robin?
Yeah.
Okay, so welcome for everyone who joined or is sitting here. Sorry for the technical difficulties. We couldn't get the mic unmuted. So we believe everything's good to go now. I'm going to be talking today about bridges. My name is Nick Nystrom. I'm at the Pittsburgh Supercomputing Center. And bridges is a PSC resource. It will be forthcoming. And its purpose is to connect researchers with data and high-performance computing. So first, a disclaimer. As I'll describe, bridges is currently an acquisition. This is in progress. And so I'm going to describe our current plan. Certain details of these slides may change over the coming months. So first of all, the name behind bridges is that Pittsburgh, as many of you know, is a city of bridges. And the system is designed to bridge to new research communities, to new fields of research. It is to bring HPC to big data in ways that hasn't been done before. And it's to bring various fields together. It will be an Exceed resource, and I'll say more about that. And it will integrate advanced memory with novel storage we developed here at PSC. And it will connect between Exceed resources, campuses, and across the nation. Bridges is made possible by NSF. It is a $9.65 million award. This award was actually made in November. And the acquisition process formally started on December 1st. The acquisition runs roughly through the end of this year. The title of the proposal was Bridges from Communities and Data to Workflows and Insight. And that really summarizes what we're doing here. We're really bringing new ways of computing to the communities that need it. HP, Hewlett-Packard Corporation, will be delivering bridges. And with that, I get to the main presentation here. So first, just for where this is set, bridges will be an important component of the national cyber infrastructure. At the NSF, there's a division called ACI, Advanced Cyber Infrastructure. They are the ones that have funded bridges, and bridges will be one component of that ecosystem. On the right on this slide, for those maybe following along in other ways, we're on slide 5. Bridges will integrate with Exceed, which is the national cyber infrastructure. Also with campuses. The picture in the middle right is of the Carnegie Mellon's Gates Hillman Center, where Carnegie Mellon Computer Science and other pieces live. And the bottom right is Temple University, who is one of the partners in this proposal. Bridges will integrate with all sorts of instruments and data. So just 3 examples are at the bottom left here. And those examples, again, these are just representative of many, many different things. The first one is of next generation or high throughput genome sequence analyzers. And these can potentially turn out terabytes of data per lab. They're responsible for most of the breakthroughs we're having now in genomics and many in medicine. This middle image is a work that PSC is doing with Harvard University for reconstructing the connectome, or essentially the structure of neurons within the brain, to find the pathways, and from there, hopefully, to find other ways of understanding how the brain works. And then the bottom, I just have as a catch-all, this is representing new ways of dealing with data. One, I actually think of it as an instrument at this point. One new source of data is the internet. And that's everything from social networks, people mining Twitter to understand issues in public health, to everything else, and then all the other things that comes from internet data. So that can also be a huge flow of data and information into such a resource, and it's where we see a lot of researchers having a lot of interest with directions they want to go. The other piece, the orange block on the bottom, is that bridges will integrate with other advanced cyber infrastructure projects. And so the ones I've called out here are the Data Infrastructure Building Blocks projects, or DIBs. We have one of those at PSC called the Data XSL. I'm not talking about that today, but people can contact us for more information. What's significant, though, is the Data XSL is functioning as a research pilot to let people get an early head start on bridges. And then there are many others that we're interoperating with. So bridges is designed to meet research needs.
Hide that bottom.
This is on my screen.
Oh, good.
Is that still safe, Robin? Okay. Yeah, I have no idea what's being shared out to the Hangout.
So you don't want to hide it from those people, right?
Yeah. So it's designed to meet research needs. And I wanted to start the talk really by saying what the machine's good for. If you're a user paying attention out there in Google Hangout land, why should you care? And so these are a few examples of the kinds of uses we anticipate for bridges. They're just examples. There will be many more. The first is to scale research questions beyond what people are doing on laptops. We've aimed bridges to reach out to new communities that have not used traditional supercomputers. They haven't done that for several reasons, and those are generally good reasons. One was maybe they didn't need it, but many fields now are being increasingly data-driven. Across digital humanities, for instance, we know that people are being pushed to analyze big data. The current trends are toward analyzing large corpuses of literature or images or other things. We've been told that people who expect to get tenure should be working with large data. If they're doing the traditional scholarship of a single author or a very narrow focus, they probably won't get their tenure. So this is very much a trend. The other reasons that people haven't gone beyond their laptop, one is environment. They want to use what they were using. They want to work on Windows or on Mac OS or something else. And they didn't want to have to learn to program a supercomputer. And then the third was just the turnaround time. For people doing certain things, they wanted to be able to try things out and see results. And when they weren't completely computationally constrained, that makes sense. And the whole idea of working a batch system, submitting a job, coming back a few minutes or a few hours or a few days later to see if something good happened is just not in their culture. So Bridge is designed to address all of those. It's designed for everyone from individuals to teams to collaborations. One thing we keep running into when we're meeting new communities, we've been talking to many recently, is people keep wondering, am I big enough? Am I worthy? And the real answer is that their projects actually are. People equate supercomputers with global climate modeling and things like that. Bridge is designed to run many more modest scale projects and to give people good turnaround for that. And I think people will find that they will scale up once they begin. Cross-domain analyses are a very strong point. In many cases, we've had silos of information. Researchers may suspect they'll be useful to other fields. They haven't necessarily been put together. But doing the data integration and data fusion to make that possible will let people ask new kinds of questions. That brings us down to the fourth point, which is shared data collections. And that's building community repositories. This could be of genomics data, it could be of astronomy, it could be of literature, it could be of anything. And being able to have that in one place for others to reference and analyze, and then having related analysis tools. Because not everyone wants to be a programmer. A lot of people want to work with it. Just as scientists would work with getting data off a telescope without having to know how to build a telescope themselves. Workflows are a very powerful concept. These really can let people have the power of HPC resources, or high-performance computing resources, without having to be programmers or expert users. Having a workflow that sits behind a web interface and starts jobs behind the scenes, if you will, rather than the individual having to schedule everything, manage all the data, is a very enabling concept. People are already doing this with certain workflows. That'll be an important part of bridges. Obviously, you need some developers, but then many more people can benefit from that. Large memory applications and in-memory databases are cases where the large memory nodes I will go into detail on really shine. This is an area where PSC has been focusing for the past 5 to 6 years with very large memory nodes, and we believe that's key to helping people be more productive. Another thing is that because bridges will have a very large computational capacity, is there are many problems in machine learning and in engineering and other fields where what we really want to do is optimization problems. Those involve parameter sweeps, they involve training over very large sets. Those can become very computationally intensive, they can involve very large data. That's also a very interesting use for this kind of an architecture. It's near the bottom of the list, but it's certainly not insignificant, is that bridges will have a very powerful collection of software and tools. For many new fields especially, having access to new software and to broad collections of software is extremely valuable. There's a lot of good work out there. There are a lot of good tools. Figuring out the best of breed is hard. Implementing them and optimizing them is also hard. If people can go to a place where they can find all of them, that's a great win. It's very much like having a smartphone now. People can't imagine having a phone that doesn't have maps. And it's these applications that make the phone valuable. In the same way on bridges, it's the applications and tools that will add value to the hardware resource. And last on this list, but obviously not last, these are just examples, is just modern, widely used software environments. And that goes back to the issue of going beyond the laptop, being able to support what people already do, but letting them go bigger and broader and ask the next questions. So in terms of concrete applications, obviously there were many when we wrote the proposal. We've come across many more in the intervening months since it was awarded. And we come across more literally every week. So a few examples are on slide 7 here. And again, these are just skimming the surface. In the first one, though, this is a very large project we've had ongoing for mining large audio-visual data, essentially video collections, and being able to search thousands of hours worth of video in seconds on a workstation once you have the database built for certain kinds of events. And that's something different that people can't do yet. We have another project here, and it was a picture in the previous slide, of understanding how the brain is connected, and that comes from electron microscopy data. It's a project with Harvard. It's anticipated to receive on the order of 100 terabytes a day of data to be processed, analyzed, reconstructed, and build essentially a geometry, a map of the brain. Looking at societal issues from social media data, being able to catch Twitter fire hose feeds for various keywords, and understand important things are happening in epidemiology, disease spread, substance abuse, all sorts of public health issues. I personally am a member of a team, a big data knowledge project, on finding causal relationships in various diseases, including cancer, lung diseases, and neural disorders, like schizophrenia and autism spectrum disorder. And the point in this is to find actual causal relationships, not just correlations. And statistically, that can be done. It's harder than finding correlations, so it's less popular, but it's important. We've had a tremendous amount of interest recently in the digital humanities. This is a field that is really blossoming. It's existed for several decades. It's really attaining critical mass now, and we've been bringing many new users on board to our research pilot system for that. Another interesting project is in organ donation networks. This is really an optimization problem with incomplete knowledge, and it will help actually save lives with getting more organs from donors to the people who need them in a timely fashion. And so the list goes on. I'm not going to go through all of them. But you can see it's a very large diversity. These span things that resemble traditional science. There's one here on astronomy. But the astronomy isn't in the sense of just what people have done before. It's in the sense of doing analyses across different wavelengths, across observations, to look at astrochemistry and the atmospheres of other planets. And that hasn't been really done. And all of these bring together elements of large data analysis, a lot of computing, in some cases novel data organization, database challenges. And so it's these kind of applications that motivated the system, the architecture, the hardware that I'm going to be describing. So our objectives were to bring HPC to what NSF calls non-traditional users and research communities. And so, like I said, these are the people who have not normally used supercomputers. And we want to apply high-performance computing, what we have decades of experience in, to big data. And we believe there are clear advantages there. And thirdly, to be able to develop ways to bridge to campuses, to help researchers scale research they are doing on their local systems, be they laptops or clusters, to supercomputers, and also back again. PSC has a lot of expertise in large shared memory. We've done this with Blacklight. It's a 2 × 16 terabyte system that everyone knows, I think, now. And even before that, with 2 large HP systems, Rachel and Jonas. And so we're leveraging that into 3 tiers of even larger shared memory that I will talk about. And then using that, that's a great building block for providing other things like interactivity and virtualization and other ways of making the system familiar and easy to use. So one of the ways it bridges is going beyond traditional supercomputing. I think, normally when I think about it, I come up with 5. The first is interactivity. And this gets away from working exclusively through a batch queuing environment. Of course, bridges will support queues too, because that's appropriate for some things. But to a very large extent, we will make interactive access possible. We'll do that through several ways. One will be going through just virtual machines, because many people who just want fast feedback aren't worried about the last % of performance. They just want something to happen. So we can accommodate a very large number of users through VMs. I also expect for certain projects, for certain uses, just as we dedicate resources now when people need it, we will dedicate resources on bridges. If people have more intensive access, they can get more performance, they can get larger memory, and so on. Second, gateways and tools for building gateways are very important. On the Bridges project, we have several partners, such as the Galaxy project out of Penn State and Johns Hopkins. We have the Mega project out of Temple University, another on molecular dynamics analysis out of Utah, and other things. And depending on the gateway, these are essentially fancy web pages, web interfaces that interface to very large resources on the back end. They allow users to start up and execute very complex jobs without having to log in, without having to manage those. And the way Exceed manages gateways without necessarily having to have their own account and proposal for Exceed resources. Those are managed by the gateway itself. And these gateways can have very large numbers of users. Galaxy advertises, I believe it's currently 50,000 users. Mega advertises 100,000 users, and so on. So this can bring a lot of people into being able to use these resources who otherwise wouldn't. Third is having dedicated resources to serve databases and web services. This is not normally part of a supercomputer. I'll talk about how those fit in. Fourth is really high productivity programming languages and environments. And by that, I mean things like Hadoop, MATLAB, R, Python. These are the things that people are using on their laptops and in their local labs. And they want to keep using those. In some cases where they really want to scale up and do much, much larger work, yes, they'll find that they have to do some things differently. We'll let them do that incrementally and take the steps as they want. And last on this list is virtualization. And that really serves several purposes. One is it lets people bring their own environments. So they can, if they have a specific installation, a specific software environment or software stack, they can bring that. And it will work. So that gives them portability and ease of use. It will also let them interoperate with clouds like EC2 and others for those who are already doing that. So the first of these new features is interactivity. This is really important. It means being able to do things either through the command line or through a web interface and have things happen. Obviously, nothing's instantaneous. Where things take a long time, you want to give people feedback, telling them this may take a while, are you sure? Giving them progress bars and the like. It lets people get work done. And we find with new communities, this is really the thing they want most. It's just when they hear this, they smile. So that works. Gateways, or what I spoke about a moment ago, the bottom examples are Gene Pattern with the Broad Institute in genomics. They're also a partner of ours. The middle one is a portal developed at Pitt Information Sciences for doing data integration and data fusion in a crowdsourcing manner. And then the bottom is Mega, which is evolutionary genetics. And it's kind of nice. It has, according to its developer, over 100,000 users, and it even has an app interface to it. So that really makes supercomputing accessible. Virtualization and containers are the next topic. As I said, this lets people bring what they want. If they're already running under something, they can just bring the environment. We also see a lot of interest now in Docker. You want to do software reproducibility. And so it fosters that sort of environment. It fosters being able to do things reproducibly, portably, and without too much additional work. The programming aspect I really can't underscore enough. Granted, not everyone will program this machine. Many will just be users of things that other people develop. But for those who are developing, whether it's their own research project or whether they're developing a resource for many others, they like these sorts of resources. We've found that the machine learning community has embraced Blacklight because it lets them access very large shared memory using Java. And their software is written using hundreds and thousands of Java class libraries. That's not going to change. The code base that the Big Data Knowledge project that I'm working on is coming from is also Java. It took me literally seconds to get up and running on both the research pilot and on Blacklight. Other tools like Python and R and MATLAB are a big part of this equation too. These are the things that people just want to work. Also for bridges, we'll be supporting Hadoop. That tends to be new for most supercomputing environments. And I really think of this as first-class support. So rather than just supporting a Hadoop cluster, as people would have at home, there will be a shared flash-based array in bridges that will act as essentially a very efficient key value store to accelerate Hadoop applications. So Hadoop here, we expect to be better than Hadoop on any normal cluster. There will also be many of these other nodes that can be configured for additional Hadoop capacity if we find that we need that. And this includes not just Hadoop itself, but the whole ecosystem. That's what matters. It's the applications written on top of it. So it's all the things like Hive and Cassandra, Spark, Project Pegasus for graph analytics, that's from Carnegie Mellon here, and so on. And so again, that will let people leverage the software they've already had written and the tools they're already using and do bigger and better things. So what's the system look like? First, I want to talk about the compute nodes. It is a supercomputer. The compute nodes are what matter. So there will be 3 tiers of compute nodes. They will have 3 scales of memory. The largest will have 12 terabytes each. That will really be among the largest coherent hardware-supported shared memory systems that one can access. And this is interesting because these really leverage what other parts of the world have done for business intelligence, business analytics. These are HP Dragonhawk servers. They were developed for the enterprise market. The R&D has been essentially driven by that market. And it's a case where the research and science community can benefit from that R&D. And so we will have these 12 terabyte servers and will benefit from all that great application or great engineer work that has been done. And what we find is that these are phenomenally good for things like genomics. We've already done some performance analysis and actually application benchmarking. They look very good compared to what we have now. Also machine learning, graph analytics, all of the things that Blacklight is excellent for now, these will be even better for. And there will be more of them for more capacity. The second tier of nodes will have 3 terabytes each. That's still a lot of memory. We're talking about RAM here, not disk. So 3 terabytes will let us do a lot with virtualization, accommodating many, many users, affording this interactivity we talked about, being able to do very large-scale visualization, analytics, things where we want to have large data sets in memory to work with together in real time. And also lots of the mid-spectrum memory-intensive jobs. Because for any kind of research, there's a spectrum. There are smaller jobs, there are larger jobs. And so will give us this overall capability to serve it all. There will be tens of those nodes. And lastly, there will be, I'll say, many hundreds of these nodes with 128 gigabytes each. There are small nodes in this little pyramid, but 128 gigabytes is still vastly bigger than most people have in their workstations. That's another thing I encounter when I talk to new users. They're just astounded by what they'll be able to do. Those nodes will be used for everything else. They'll be used to execute components of workflows where people want to start up hundreds or thousands of different jobs to get an overall problem done. They'll be used for interactivity. They'll be used for Hadoop. They'll be used to house GPUs and other special resources and to serve overall capacity. Because overall, this machine will still be good for anything that requires large memory. And where large here is 120 gigabytes, that's still significant. These nodes will feature the latest Intel Xeon CPUs and the latest NVIDIA Tesla GPUs. And they'll be the dual GPU maximum performance variety. All of those I'll be able to say more about over coming months. Along with the compute nodes, Bridges will also have special nodes dedicated to just doing databases and web services. And that's new. These won't be just layering this on top of the compute nodes. These will be nodes for this purpose. And we've found this to be essential. We've done a lot of work with the, for instance, the genomics community, where databases are key to making new strides in genomics and in personalized medicine. So we will have a variety of nodes. They will have SSDs in them, where high IOPS are most important. There will also be nodes with rated hard disks, where people really want good performance, but also much, much more capacity in the terabytes. And those will serve a variety of databases. I just caught a bunch of the logos of things we know we're going to support here. Again, these are examples. It's not exhaustive. But it just gives you a flavor for what all is going on. There are relational databases like Postgres and MySQL. There are document databases like CouchDB and Monet. CouchDB and Mongo. There are column stores like Monet. There's SciDB out of the group that has seen value in array stores. And these will just be very valuable for all sorts of projects. People have been struggling with managing data, doing data management plans, and figuring out how to get at data, make it reusable, make it shareable, and deal with the metadata, describing what's in there, making it available to others. And these will help a lot with that. They'll also help to drive the gateways. A difference between gateways and the old style batch way of doing things is the gateways want to be running 24/7. At any time in the country, people are going to be awake and working with them. Even within PSC's walls, we have people who are nocturnal and prefer to work at night. And so it's essential these be running 24/7. Databases are what serve them. And so having those always running in a persistent way is essential. The dedicated web servers will make that possible. These will have 10 gigabit links to the external world. They'll enable service-oriented architectures. Aside from just having these things implemented within Bridges, we also find increasingly people want to do distributed systems where they have parts of the system running at their home institution that would then interact with PSC, and this is already happening, by means of HTTP transfers, JSON messaging, and other things to query, to make queries, to exchange data, and so on. Data management underlies all of this. And so Bridges has a variety of ways to do that. It builds on things we've learned at PSC. The first is a very large shared parallel high-performance file system. This builds on the /2 work we've done here. Many of the people in this room and on the internet know that from the data supercell is a production disk-based system we've had running for around 3 years. The data exascell, which is the research pilot I've mentioned, it builds on that and extends /2 and the file system work we have done. And Bridges will build on all of that. So this will be a file system that will be visible to all nodes. It's useful for persistent, very large shared access to storage, community repositories, very large data sets. Again, those could be from an individual researcher. It could be for a community. Doesn't matter. Complementing that will be distributed storage. And by that, I mean there will be storage on each node. And there are 3 good reasons for doing that. The first is that many new applications, especially from the NoSQL database world, expect storage to be, they expect to have local storage. They expect to shard things. And the choice is either provide them with local storage or somehow modify all those applications. It's a lot easier just to use what exists. It's easier for users. It's also more economical to run the system. So that's portability. There's also performance. By keeping your storage local, other institutions have found that greatly improves overall system performance. It lets people do I/O where it belongs. What that means is the third point is it improves performance consistency. So not only do you reduce, by having local storage, not only do you reduce the load to the shared parallel storage, you also reduce the burstiness of it. And so what you don't want to happen, you don't want your performance to the shared storage when you actually need that to change dramatically just because somebody else is doing something that you can't see. And having other people do many things locally lets the performance to the shared storage be more consistent. And last, there will be the shared flash-based array. I mentioned that in conjunction with Hadoop. It will also, in some cases, it may be beneficial to databases. And to that extent, Bridges is, we know will be useful in many, many ways. It will also be, in some sense, a research system. NSF is a research organization. And we will see how else we can use that flash-based array aside from Hadoop and where it can benefit. But we know that having tens of terabytes will be good. Connecting the whole system will be a new fabric, or new network, if you will, from Intel called OmniPath, or the Intel OmniPath Architecture Fabric formally. So OmniPath is an evolution of networking research that Intel has been doing for a while. It is brand new. It's not Ethernet. It is not InfiniBand. It will be, we believe, better. It will be the highest bandwidth that we can access at that time. It will have optimizations for applications written in MPI, PS languages, and other things that people already do use. And it's forward-looking because it's an integral part of Intel's roadmap. If you look this up on the web, you can see how they plan to work it into future CPUs. So this schematic of what the machine looks like builds in all the concepts we've talked about over the past few minutes. So at the bottom are the compute nodes. And in the compute nodes, the area of each square is proportional to the amount of RAM on the node. So the 128 gigabyte squares on the right are smaller, 4 terabyte, or 3 terabyte, and 4 terabyte. And then the number of squares is approximately proportional to the number of nodes of that type. And so this gives you in a way, an infographic of how many nodes there are, the relative sizes, and the amount of memory available to each. Those are all connected by the OmniPath fabric, this blue oval in the middle. So they'll provide very high performance connections to the overall system. And it's a topology, again, that we have designed. That was actually, it's a combination of making the best of the fabric with the design points of the system to bring the most computing to bear on this type of problem. The project file system is the large parallel file system that we discussed. Very high bandwidth, very low latency to many petabytes of data. So everything will be able to see that through the OmniPath fabric. Those will also connect to the database nodes, the web server nodes, and nodes I haven't mentioned before for doing data transfer. And these will mainly be used just to help with bulk data transfers from the network, from instruments, from other sites into bridges and out. And then all of that will connect to exceed the campuses, the instruments, clouds, and everything else you can imagine. We currently have a 100 gigabit link going out, and we can use bandwidth as we require. The target schedule for bridges, as I said, this is the start of an acquisition process. We've begun. Because the target for production was stated by the foundation as being January of 2016, that is our target for production. Working backward from that, we wanted to get in the best available technologies for the lifetime of bridges, and so that means we'll start construction in October. That'll let us get in the best CPUs, GPUs, OmniPath, and other things, other pieces that we want to be available in bridges. Before then, well, once that starts, we'll have an early user period. Before then, which is now, we're already working with communities on identifying likely projects, on building interest, and on raising awareness. For people and projects that want to begin work, who have data-intensive challenges, especially that stress data analytics in new ways, we do have this research pilot, the Data XSL, and we get people started on that. And that can happen immediately. That has been running for 1 year. And so with that, I'd like to just leave contact information. There's a website, psc.edu/bridges. On that, we will be populating it with more information over the next weeks and months as the project evolves. I'm the PI. I put my picture on here for people who are on Google Hangouts and don't know me, so if we run into each other in the hallway, it's always good to have a face. Co-PIs are Michael Levine, Ralph Roskis, and Ray Scott, who are all here. Of course, it's supported by lots and lots of PSC people, basically the whole staff in one way or another. So I'll take it to questions for there. I believe we're scheduled officially to 3:30. Yes, Brian.
Hey, Brian Stenley, University of Pittsburgh. Congratulations on your award. Very
Thank you.
exciting. Can you compare and contrast, either from an architecture standpoint or maybe from an operational standpoint, how Bridges is going to compare to Jetstream and CloudMap?
Okay, so I suspect people can hear, so I'll repeat the question first. The question was how Bridges will compare and contrast to other new systems, namely Jetstream, which is a project out of Indiana, in Tech, and Cloud Lab. And Jetstream especially was awarded under the same solicitation as Bridges, so they were announced at roughly the same time. Jetstream is really aimed to be a cloud. It is aimed to be the first NSF production cloud, analogous to other commercial clouds, but for NSF research. Bridges, although it has a cloud-like component in terms of virtualization and being able to fire off virtual machines and interoperate with clouds, is not a cloud project per se. It's much more about bringing real high-performance computing nodes, I believe, and this is, I'm not sure of this, but I believe that Jetstream is being built from Dell servers, whereas Bridges is being built from very much larger, purpose-built, memory-intensive 3 and 12 terabyte servers along with other nodes. So we're aimed much more at being able to do tightly coupled, very intensive computation rather than just cloud work. Cloud work tends to be more decomposable onto individual nodes. One word was embarrassingly parallel in the past. So it's a different kind of research. We're looking much more at very large-scale data analyses, very large data repositories, tightly coupled computation, large memory computations, like genome sequence assembly, machine learning, and graph analytics, social network analytics. Those are things you can't really do effectively on clouds because as algorithms don't partition, you can't really break them up as well. So that's the main thing. Cloud Lab, I know less about that. I know about Jetstream. But I believe it's more of a cloud development project, whereas Jetstream is cloud production. So yeah, we have a cloud flavor, but that's not the emphasis. And of course, we've been talking to Craig Stewart with Jetstream from the time these awards were made and before that. And we expect to continue talking and collaborating and working together as it makes sense. They're really complementary. Joel, you had a question.
Yeah, you showed in your diagram the web server and database nodes as being separate, but I gather they just sort of are from the other pool of nodes and are temporarily repurposed in and out of that service. So
the question is the separation of the database servers and web servers on slide 19 from the rest of the nodes. In fact, they are separate nodes. There is separate hardware. It's not the amount of hardware does not rival the amount of hardware in the compute nodes at the bottom. There's what we believe will be sufficient for people to make substantial progress and to house a number of projects. If the demand for the web servers and database nodes were to exceed the number of nodes that we right now think will be needed, of course we can repurpose other nodes from the bottom for that purpose. So we have a lot of flexibility there. It actually raises a question about overall allocation of bridges. So we've talked about VMs, we've talked about interactivity, and we've talked about workflows and other things. And so we expect that to be another area. We have a lot of experience at PSC in scheduling. And so we expect to be able to basically tune the balance of nodes, say in this 120 gigabyte pool down here, and be able to tune the balance between number we have serving interactive uses versus number of serving workflows or batch uses based on demand. And I expect that to change from month to month or even week to week. So the short answer is there will be dedicated resources to the top. Every block here does represent a different physical instantiation of something. And the amount on top is substantial. We'll see if it's enough. If it's not enough, we'll make adjustments. But for instance, it's only in the database servers in the top where we have SSDs for solid-state disks. The distributed storage in the nodes down here will be hard disks for more capacity.
And there's a different network connection for those nodes.
So the network connection to nodes on the top, the database nodes will probably have gig-E connections to the web. Web servers will probably have 10 gig-E connections, 1 to 10. And we'll decide how we apportion it between web servers and data transfer nodes. But there will be multiple 10 gig-E connections to the world, and there will be more 1 gig-E connections to the world. All of these will speak through OmniPath to the system. And so, yeah, that's the plan. But it's a plan. As Sergio likes to say, no plan survives contact, so we'll see.
No, we're almost said that. So.
Well, you like to quote him.
We don't have that now.
Yes, great.
Because of the diversity of applications on the system, it sounds as though there's going to be a lot of software maintenance required. Do you expect the user community to be doing all that software maintenance?
The question was, because the system will be so diverse, there will be a challenge with software maintenance. And yes, there's a lot to do there. what we're finding now on the data XSL pilot project is that almost every new group we talk to has something new they wanted added to the environment. I'm hoping this converges at some point. But in reality, people will have, we're seeing several things. There's a lot of community software. We have different types of users. Sorry to be glib before. But we have the developers who know exactly what they want. They did it. We have people who are fairly sophisticated users, and in some cases, they want their own VMs. They want to install different instantiations of some database or other to do different things for their research. They're fine doing their own maintenance. And for people like that, having VMs is an advantage because then they can just go and do it. There's the other group that just wants to use what everyone else produces. For that, we have a combination of things. We have expertise with the developers of gateways and applications. That's external. We have PSC's own staff, our user services group, who know a lot. The people who are working now with the research pilot, who are doing installs now on behalf of users. We are building technologies for helping with automating installs, so when a new release of something comes out, we're making that easier and automated so that people don't have to do it every time, unless a problem arises, obviously. For bridges, we also will get additional support. We will be posting 2 positions. One will be a data analytics specialist, one will be a workflow specialist. Those will work with and help communities to develop, install, implement, optimize applications. Obviously, they also have expertise when it comes to helping with maintenance. And we expect to have a 3rd position on the system side. And those we'll have out basically as soon as we can to start trying to find the best candidates. But software maintenance is always a challenge. It's one where I think we'll always be challenged with this project, but it's unavoidable. I would add one more layer to that, and it's not just installing and maintaining the software that you know you want. It is being aware of communities and what is new that's coming out, because a lot of this is a very rapidly evolving landscape. Sean.
So from our experience with some of the public health projects that are using service-oriented architectures, how do you, are you planning in the software phase of this to provide some sort of common API through the services that, say if I'm running an external service that just wants to be able to connect to the compute, is there some part of this project that gives me that capability versus me having to roll my own for my individual web service?
This question regards external individuals or software services that want to connect with bridges as service-oriented architecture. And so there'll be different approaches to that. One is we're definitely developing APIs. The Big Data Technology project I'm working with is one such project. In that one, we're enabling software for doing causal discovery, really identifying what causes in big data, or what variables in big data are actually causes of effects in the data set. And for that, for example, we anticipate having a web-based interface that will run on everything from laptops to mobile devices. They can run things locally where that's appropriate, or it can farm them off to PSC resources, including bridges, when it's either hitting a very large data set that resides here, or when the calculation itself is big. And so we're developing APIs for that. In the research pilot, which is all about building blocks, I expect that to be one of the deliverables there. It will be APIs for doing that kind of thing. There are also, in many cases, these connections to things like databases, those APIs exist in terms of just doing queries across some port. And that brings up an interesting point, and that is that on top here, the database and web servers on slide 19, some of these, for various purposes, want to be outside the firewall. For others, one will want to open ports to specific databases through firewalls. Because a lot of these services have let's call it insufficiently explored security. There'll be advantage to running a lot of these in virtual machines to compartmentalize risk. And so we're already doing that. The information integration architecture of PIT goes across the web, HTTP requests through holes in our firewalls to Neo4j and MySQL servers. And so I think we'll find some common building blocks and APIs that we'll certainly share and make available and document. In other cases, there will be things that people just want to do that will be purpose-driven. And I think we'll see both. But this talk is also resonating with groups we talk to. And the reason for that is they are finding on their local campuses a lot of pushback because, first, maintaining their own servers is problematic, especially for these shared data collections where they want to do large collaborations. They want to have servers that they can do things on, so they essentially want root-like access. They'd love to have a VM. For them, that often means now trying to deal with a server that's not in their lab anymore. It's off at some other compute center. And we can make that easier. It also means dealing with their own campuses. They're well informed. Their network policies, and they say, well, this software is really suspect. We can't deal with it. And that makes sense. But the way we're planning bridges with VMs and other things, we can deal with that because we can compartmentalize it and still maintain data security for everyone else. Yes, Bob.
I presume we can't have a single service unit that someone would ask for in a proposal to the XRAC. How far along are we in defining what people will ask for? I mean, I want to ask for so many transactions. I want to ask for so many core hours.
The next question relates to how will people request allocations on bridges in terms of resource limits. Right now on Exceed, people ask for what are called service units, which basically maps onto core hours of computing. And obviously for bridges, it's a unit. It's not the only fundamental unit. It's not the only interesting unit. We will have to. Core hours are still important. How many core hours do you need to do your work? But also, how much data will you have to store? How much data will move? Will you need access to databases? How large will those be? Will they be IOP dominated? Will they be capacity dominated? Will there be web services needed? Will you have to have a web server of your own? These are great questions. On the data XSL, this research pilot, it's giving us a great environment in which to figure these things out. So on the data XSL, we are now accounting for as many of these things as we can and building in accounting for more of them. So we can start understanding how best to measure what people actually do. And once we understand what we can measure and the kinds of things they're doing and how those things actually correlate with their research, then we can start figuring out what guidance we would give them when it comes time to write proposals for bridges. I think the first round of proposals for bridges will be due in September. Is that right?
Well,
For a January allocation?
Correct.
Okay.
In a sense, already people who go to this next meeting are going to probably be grandfathered into bridges, but we don't have to tell them.
Right.
That's right.
Right. So we'll figure out what kind of guidance to give. We'll obviously have to work with Exceed on a number of factors. One will be how to do allocations. Another will be what sort of reporting comes from bridges to Exceed. So, for instance, Exceed right now has certain ways of understanding what software is available on machines. And we'll have to look into a lot of this. It's a new kind of computer. It's designed for new communities and new uses. That's all progress. That's the way things should be happening. And we'll have to evolve how we deal with it accordingly. And that we do have to do all these new things says we're probably doing some things right in terms of it not being a traditional supercomputer. If people have ideas on this, I'm always open to brainstorming. Are there any other questions or anything from Google, Robin? Okay. Okay, so I believe this recording will be made available on PSC's YouTube for the future. I hope to have it available to point people to in other parts of the country. In terms of spreading awareness, I know I plan to talk to campus champions at the SEED conference. There will be other conference presentations, other opportunities to talk to users. We've been reaching out individually to people. Rick Costa has been very instrumental in that, going to digital humanities groups. And so please help to spread the word, by whatever channels you have, and let people know these good things are happening. Yep, thank you.